welcome back to the next edition here. As we were discussing the controlled buffer register with an active high clear. In this case, a little bit, a recap here, that we have 4 D flip-flops, that is, we can store a maximum of 4 bits, and combination of 4 bits is what we know as that they can go from 0000 to 1111. So in decimal terms, we can store a 4-bit word anything between 0 and 15. 1111 means decimal 15 and 0000 means 0. We have seen the circuit. From the circuit, it is clear that the input we have, in the input of all the D flip-flops, we have put some control, unlike the previous case wherein we were just feeding in data and removing data. So the control here allows us to store the data in this shift register as and when we want. That is, the shift register can store data, and despite having change in its inputs, the same data would be stored or given out to us, so it acts as a memory element. And when we want to replace or create a new memory, then we can always feed in data. Now this concept is achieved and is explainable by looking at the diagram. In the diagram, we see that the OR gate input to the D flip-flop is governed by the inputs to the OR gate. Each OR gate is a 2-input OR gate, and it is getting its data from 2 AND gates which are fixed above it. In one of the AND gates, we find that we have the data input. Data can be A3, A2, A1, A0, B3, whatever way we want to designate. It can be X3, X2, X1, X0, or B3, B2, B1, B0. And in the other AND gate, we see that it has the output of the D flip-flop being fed at its input. It is important to note that there is a common signal load, which is actually the control for the shift register. For the AND gate on the right, load is fed directly in all the 4 flip-flops, that is D3, D2, D1, D0, whereas in the left AND gate, we see the complement of load signal being fed from D3, D2, D1, D0. So effectively, it allows us to infer that at a given point of time, only one AND gate would be working and the other AND gate would be inhibited, that is, its output is fixed at 0. Because the load signal or the control signal can have only one value at a given point of time. Now we look at the figure very carefully. When load is equal to 0, then all the AND gates of D3, D2, D1, D0, AND gate means the AND gate on the right as seen on the screen. When load is equal to 0, then all the right AND gates are disabled, because even if one input is 0 for any AND gate, the output is 0 for that AND gate, because typically the Boolean expression of AND gate defines that AND gate gives a high output if and only if all of its inputs are high. There could be 2 inputs, there could be 3 inputs, there could be 10 inputs, there could be 100 inputs, but the output of the AND gate will be high if and only if all of its inputs are high. And we know that for 2 input AND gate, if one of the input is A, then A dot of 1 is A. That is A AND with 1 is equal to A, because if A is equal to 0, then 0.1 is 0, and if A is equal to 1, then 1.1 is 1. So when load is equal to 0, then all the right AND gates located on the right in the screen are disabled. So new input, the inputs we can see as x3, x2, x1, x0, they do not come out of the output of that AND gate and as input to OR gate. Whereas all the AND gates on the left are enabled, that is, load complement is equal to 1, and therefore they pass on whatever is the other input as its output. Looking carefully, we find that if it is the value Q3, Q2, Q1, Q0, which are the outputs of the flip-flops D3, D2, D1, D0. So hence, the OR gate has two inputs now. When load is equal to 0, it has inputs from left AND gate and the right AND gate. The left AND gate gives for the first flip-flop, that is D0, the inputs to its OR gate are Q0 plus 0, which is Q0. Q0 ORing with 0 is Q0, and therefore in the first clock pulse after starting, we have the new input of D0 as Q0. This way, the new input of a D1 is Q1, the new input for D2 and D3 is Q2 and Q3. So we find that it goes around in a circular fashion, and till the time the load signal is 0, the shift register keeps shifting the same data. This implies that this shift register will always give the output Q3, Q2, Q1, Q0 as equal to Q3, Q2, Q1, Q0 till the time the load is 0. That is, this shift register will behave as a memory. Clear? So what we have here, that till the time load is equal to 0, this is buffer register is just an enhanced memory element. It could be 4 bits, it could be 10 bits, it could be 100 bits. So we all know that no change occurs till the time load is equal to 0. When load signal goes 1, then the load signal complement would be 0, and hence the AND gates located on the left would give its output as equal to 0, irrespective of the values of Q3, Q2, Q1, Q0, which are input to the left AND gates. And in this case, the AND gates on the right would have at its inputs x3.1, x2.1, x1.1, x0.1, and hence output of the AND gate would be x3, x2, x1, x0. So input of the OR gate would be 0 plus x3, 0 plus x2, 0 plus x1, and 0 plus x0. Hence, output of the OR gate would be x3, x2, x1, x0, which would be the new data for the D flip-flops D3, D2, D1, D0. Hence, when load is equal to 1, the output of the flip-flop would change from being Q3, Q2, Q1, Q0 to x3, x2, x1, x0. Hence, when with load equal to 1, we would have Q3, Q2, Q1, Q0 as equal to x3, x2, x1, x0. So, when load is equal to 1, we can feed in new data to this buffer register, whereas when load is equal to 0, then the old data that is already present inside this buffer register is stored as memory element. Summarizing, load equal to 0, buffer register acts as a memory element. Load equal to 1, the buffer register is ready to accept new data. So when clear, in this case, how do we feed in new data? For new data, we also use the function clear. When clear goes high, then all the flip-flops get reset and Q3, Q2, Q1, Q0 reads as 0, 0, 0, 0. This is necessary when we have to use the same configuration for counting. Like we said, when we go to fill the petrol or fuel in our vehicles, we ensure that the counter is reset to 0 before we start refilling fuel in our vehicles. And that is the role of the clear. Clear ensures that it clears out all previous data from the memory, in this case the buffer register. Same in calculators also. When we use calculators, we clear out the memory and put in our new figures as our new memory. So once we give clear as high, it cleans out all previous data from the flip-flops, in this case D flip-flops, and it resets them to 0, 0, 0, 0. When clear goes low, then the register, in this case the buffer register, is ready for new data. In this case, we have to ensure one thing, that the clear should go high, but that should be only temporarily. Till the time clear remains high, even if we feed new data to the flip-flops, they would just give out 0 as the output, because any new data comes, it is cleared out and only 0 remains. So for shift register to function properly, we need to have the outputs changing state, and for this the clear has to go low. So we see that we have a clock, we have a clear, we have a load. These are the three functions based on which the shift registers work. Clear has a very specific purpose, and which is that it clears out old data, and then you have to make the clear go low so that it does not clear out any live data that you need to feed in. The clock can be configured such that the D flip-flop, in this case the D flip-flop, changes state at a positive edge or the negative edge. That is user defined. Finally, the load, we have seen that when load is low, the bits, that is the input bits, in this case x3, x2, x1 and x0, they cannot reach the flip-flops and new data cannot be entered in the flip-flops, and the flip-flops combination here, the 4-bit flip-flops we have as the binary word, acts as a memory. The moment we keep load signal as 1, it forces the output to feed back to its data input, and at every positive edge of the clock the data is retained. We also have the shift registers. Till now we just had the register, and now we have shift registers. The importance of shift registers is mainly in the case of counters. The shift register has another function as shifting of data, which may be shift right or shift left. So hence the shift register moves the stored bits left or right, and the bit shifting is essential for certain arithmetic and logical operations, which is the basis of all microcomputers. Microcomputers are the building blocks for all large computers. They are the basic alphabets, if I may use the word. With these alphabets, we can make a paragraph or an essay. So, importance of microcomputers is paramount. So, a diagram of a basic shift register shifting left is shown in this case. Again, we have 4 D flip-flops connected in series, and in this case we have only one single data input, that is D0, which is affixed to the LSB D flip-flop. What we have here is the D input being fed to the first flip-flop at all clock pulses, that is either rising edge or falling edge. We would have the data being shifted from one flip-flop to its next flip-flop. So, if you look at the diagram carefully, we have the D input, the first D input to the first flip-flop. It may be a 0 or it may be 1. So, initially, if we have clear, then the inputs, or I would say inputs that are seen at the outputs, is Q3, Q2, Q1, Q0 as equal to 0, 0, 0, 0. So, if the data is cleared out and we have 4 zeros, then it makes sense to feed in the first data as 1. Otherwise, we are unable to distinguish between the current 0 and the next 0 that is going to be fed as the data. In order to test whether the circuit is functioning or not, we feed just one input of the D0 flip-flop as 1, a binary 1. Then initial state of Q3, Q2, Q1, Q0 is 0, 0, 0, 0. At the first clock pulse, it would be 0, 0, 0, 1. This 1 is the data input that has been fed just once and stopped. At the next clock pulse, we would have 0, 0, 1, 0, because now the new data would shift from the LSB to its next flip-flop, that is D1, and hence Q3, Q2, Q1, Q0 will be 0, 0, 1, 0, because Q0 will shift to Q1, Q1 will shift to Q2, and Q2 will shift to Q3. An old value of Q3 would be lost in the process. Here we have made an assumption that the first D0 as the input just gave 1 as the first input and then it went 0. So third clock pulse will give us Q3, Q2, Q1, Q0 as 0, 1, 0, 0. Fourth clock pulse will give Q3, Q2, Q1, Q0 as 1, 0, 0, 0. Fifth clock pulse will have Q3, Q2, Q1, Q0 as again being reset to 0, 0, 0, 0, because at the fifth clock pulse the data input or data available in D3 would be lost as per this figure. So in this case we find that the data is seen to shift from right to left. Why? Because the D0 was fed to the first D flip-flop in this case. So summarizing, we can say that the DN sets up, that the data input sets up the first flip-flop, Q0 to the second, Q1 to the third, and so on. So when next positive edge strikes, the stored bits move one position to the left. So initially when we make this DN as 1, we get the values of Q3, Q2, Q1, Q0 as 0, 0, 0, 0. That is, after the clear had gone high and then it went low. So the first positive clock edge sets the first flip-flop and we get Q3, Q2, Q1, Q0 as 0, 0, 0, 1. Next clock edge arrives. If we do not reset the DN to 0, then at the next clock pulse we would get Q3, Q2, Q1, Q0 as 0, 0, 1, 1. Third one will give you Q3, Q2, Q1, Q0 as 0, 1, 1, 1, and the fourth clock makes it Q3, Q2, Q1, Q0 as 1, 1, 1, 1. So we've discussed both the possibilities that D1 becomes 1 momentarily and then it goes 0, and in this case the one that we discussed recently we made D1 fixed at 1. So in the previous case, when Dn became 1 momentarily and went 0, after the fourth clock pulse, that is the fifth clock pulse, we got Q3, Q2, Q1, Q0 as equal to 0, 0, 0, 0, whereas in this case, when Dn remains 1 permanently, we would get, even after the fourth clock pulse, we get Q3, Q2, Q1, Q0 as equal to 1, 1, 1, 1. And after this, any number of clock pulses can come and the shift register is able to retain the value at Q3, Q2, Q1, Q0 being able to is stored at 1, 1, 1, 1. The typical timing diagram for the shift left register is shown over here, and you can see that D and the Q values are in sync with one another. Typically the shift right register is shown over here. In this case we have not changed the configuration of the flip-flops, but only we have changed the wiring of the flip-flops. So in this case you'll see that the DN is fed to D3, output of D3, which is Q3, goes as input to D2, output of D2, which is Q2, goes as input of D1, whose output Q1 acts as the input of D0, and finally output is seen at Q0. So again, beginning from the very scratch, initially we have a clear goes high, it changes, or rather the output of the flip-flops, that is Q3, Q2, Q1, Q0, goes as 0, 0, 0, 0, and if D in is equal to 1, then we have, after the first clock pulse, we have the output Q3, Q2, Q1, Q0 as 1, 0, 0, 0, 0. If Dn does not change its value from 1 to 0 and remains 1, then at the second clock pulse we will have Q3, Q2, Q1, Q0 as equal to 1, 1, 0, 0. Third clock pulse will get Q3, Q2, Q1, Q0 as 1, 1, 1, 0. Finally, at the fourth clock pulse, we would have Q3, Q2, Q1, Q0 as equal to 1, 1, 1, 1. So, shift right register functions in the same way as shift left register. The only thing, the movement of the data is just the opposite as that of the shift left register. So finally, looking at the points, we see that it is the user who defines, user means us, who defines in which direction data is to be shifted. And in next session, we will be starting off with what is known as the controlled shift register, wherein we'll see that amount of control we have introduced artificially. And this is the place where all concepts of artificial intelligence gets built into the circuits. Controlling the hardware by means of software commands is how we incorporate the element of artificial intelligence within electronic circuits. Thank you so much.